Hi everyone, welcome to section 10.2 arc length of a parametrized curve. Number one, parametrization of a curve and the arc length formula. As you know, there are things that are in space and the path of a moving article. They form a curve, but the curve cannot be described by an equation y equal fx. To model the movement of such particle in space, we used parametric equation. And the parametric equation has the form x equal ft, y equal gt, where t is the parameter. For each t, we will be able to determine a point x, y in which we can plot. And as t vary, the point x, y will trace out a parametric curve C. Now come the arc length formula. In the previous lesson, we see that for a curve C from, let's say, A to B here, if we take a look at a small arc ds and blow it up, then we see that, well, it does look like this ds right here. And so we can get a right triangle. Small change in x, small change in y. Using the Pythagorean theorem, then ds is ds square. Dx square plus dy square. Introduce the dt in there because x and y are function of t. So this would be a dx over dt times dt square plus dy over dt times dt square. And then from there, we see that, oh, we can factor out the dt square. About dx over dt square plus dy over dt square. And dt square. So this still ds square. So ds would be the square root of this, and that would be square root of dx over dt square plus dy over dt square multiplied to dt. So for t between alpha and beta, then the length of the curve C would be the integral of C ds, and that would be the integral from alpha to beta. Root of dx over dt square plus dy over dt square multiplied to dt. Ah, what a nice formula. Let's take a look at how we apply the formula to computing arc length of parametrized curves. Example, compute the length of the curve parameterized by t x equals sine t, y equals cosine t, where 0 less than equal t, less than equal pi. If we plot this, then this is exactly half of the circle going from -1 to 1. And this is the curve C. We did it in the previous lesson. Now we just used a different method, parametrization, to do it. Let's take a look at a small arc. ds is root of dx over dt square plus dy over dt square dt. Derivative of x with respect to t is cosine t. We have a cosine t squared plus derivative of cosine is negative sine t squared and dt. Well, cosine square plus sine square is root of 1 dt. So this would just be dt. Oh, how amazing. Huh? The length is integral over the curve C of ds, which is the integration t go from 0 to pi. So 0 to pi dt. And if you don't see anything here, that's the number 1. And the derivative of 1 is t. Evaluate from 0 to pi. And this gives us pi. Example, compute the length of a curve parameterized by t. X equal t minus sine t, y equal 1 minus cosine t, where t is between 0 and 2 pi. Some curves are very difficult to sketch. For example, this one. So let's not sketch it out. And we can compute the length of the curve by figuring out what ds is. It's root of dx over dt square plus dy over dt square dt. Ta-da! Derivative of x with respect to t, 1 minus cosine t square. Derivative of y with respect to t, sine t, then square it dt. Okay, I'm going to FOIL it out here. 1 minus 2 cosine t plus cosine square t plus sine square t dt. Well, cosine square plus sine square is another 1. 1 minus 2 cosine t plus 1 dt. So we have 2, right? And then we can factor the number 2. 1 minus cosine t dt. This integral is a little difficult to evaluate directly if you do the integral of this. The trick here is notice that sine square theta is half of 1 minus cosine 2 theta. Use the identity and we're going to have a root of 2 multiply to 1 minus cosine t is the same as 2 sine square of t over 2 dt. And now you can see that root 4 is 2, right? And then sine of t over 2, if you do the substitution, you will see that that is sine go from 0 to pi, and sine of a function from 0 to pi is positive. So we don't need to use the absolute value. 2 sine t over 2 dt. Very cool. Okay. Once we have the ds, then we can compute the length of the curve L, integral over the curve C, ds 0 to 2 pi 2 sine of t over 2 dt. And there's just a quick use up. So this would give us the -4 cosine t over 2 evaluate from 0 to 2 pi -4 cosine of pi minus cosine of 0. So -4 cosine of pi is -1, cosine of 0 is 1. Well, that is -4 times -2, which is 8. Okay. One more. Compute the length of the curve parametrized by t. X equal e to the t minus t, y equal 4 e to the t over 2, where 0 less than equal t less than or equal to 2. We can first get the ds here. Root of dx over dt square plus dy over dt square dt. Yay! Let's take a look. Derivative of x with respect to t is et minus 1 square. Derivative of y with respect to t is the 4e t over 2 multiplied to the derivative of the inner function, which is 1 over 2 square dt. Yeah. Work it out. So this one is the e t times et is just e2t minus 2et plus 1 plus we have 2e to the t over 2. So 2 squared 4 and et dt. Okay. Simplify this and we will have a e2t plus 2et plus 1 dt. Oh, the lucky thing is that we can factor this out. Et plus 1 square. Well, e to the t is a positive function, so we don't need the absolute value. Square root of the square is e to the t plus 1 dt. Oh, how nice. The length of the curve is integral over the curve C ds, which is integral from 0 to 2 et plus 1 dt. And that is et plus t evaluate from 0 to 2. That gives us the e squared plus 2 minus e to the power 0 plus 0. Well, e to the power 0 is 1, so e squared plus 2 minus 1, which is e squared plus 1. Awesome. Thank you for watching. I hope you find the content useful. Please like, subscribe to help the channel grow. I'll see you in the next video.